Welcome. Thanks for coming. So I had a thought the other day, and the idea was about these conditional jumps that maybe some of them execute faster than others. And particularly the reason why is because some of these will look at just one bit of the flags register and for the comparison, and some will look at 2 bits of the flags register and have a larger expression. And I was thinking that these ones would run a little slower than the others just because they're doing more work. And that's what this video is going to be about. So let's go take a look. Here's the program, the test program I wrote. And we're not going to look at that first. First we're going to look at the results. So let's just go ahead and run them. You can see here that when it ran, JL 1.01. That's a normalized answer where the fastest one, JE, was 1.00. So JL being 1.01 means it was just a fraction, 1% slower, which I can buy that. I've run this 3 or 4 times and it seems to always be 1% slower. Can I live with 1% slower? I can actually. JLE 1.01. That's a little more complicated expression, 1% slower. JG, it's a more complicated expression, 3% slower. JG, just comparing, it's like a simpler expression, 1.00. Actually, I kind of thought the results of my tests didn't prove my concept at all, but it almost kind of did. It's just not very much of a difference. You'd have to run this test. Well, let's run it again, I guess. Let's run it again. Because you could say that this JL is a complicated expression because it's comparing 2 bits. And this has got an OR in it, and it's 1.02. And this has an AND in it, it's 1.01. But these others down here, and a different one landed at 1.00. I don't know. I think the results are maybe inconclusive, and the difference is minimal. But that's not the point of the video. So if you're interested in whether some jumps were faster than others, overall, this test says no, not really. And you can leave the video now because the answer, there you have your answer. If you want to watch and see how the test was made and how you can test how I tested such a thing, then let's keep watching because that's what we're going to go over now. So, here's the program. We enter in to a console window and we run a function called main. Here's main. We have an array called times that's going to, it's 10 DQs. It's a buffer of 10 DQs that we're going to collect all our times in for our tests. Here's a function called run test. You pass in it the address of a function that you want it to run. It collects in the RX register how long it took to run the test, and the length of time isn't really time, it's CPU cycles. So essentially it's a number of cycles it took to run the test. So every computer will have a different number. But the idea is that they'll be relative on your computer. We increment the array indexing variable, and we go to the next test. Now, these 1, 2, 3, 4 lines are repeated 10 times, once for every test. The only difference is which function is being passed into this function called run test. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 tests are ran. Then I run a function called find least on the array on the buffer to find out what's the fastest time. And then I do this normalize, where it figures the normalization number, and it starts kicking results out to screen. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the program ends. So let's look at the function called run test. Run test sets up a number of iterations at 1,000. So it's going to run each test 1,000 times while the clock is running. So here's my function, my module called CPU timer. It starts the clock, starts the cycle counter, maybe you could call it. This is where we call the address of a function. And we increment our iteration counter, and we do a comparison for the bottom of our loop. We do a jump. Jumps up to this line and repeats the test. So the test gets ran 1,000 times. After the 1,000 times, it stops the CPU timer, and it does the get difference function, which puts in the RAX register the difference in count between the start and stop, and we exit the function. Now we're going to look at these test functions, which are actually very simple as well. You're going to see I'm going to move dad into the RX register, and we'll see why I do that here in a minute. I use that for debugging purposes. It doesn't have any reason of function for the actual program to run. It's just for the debugger. Now, what I need to do is I need to set the flags bit and set flags register in such a way that this jump will happen, because I need to make sure every test performs the jump. Either they all perform the jump or all don't perform the jump. In this version of the testing, they're all performing the jump, which is considered slower, and I can live with that, as long as it's consistent. So, like for example, this moves 1 into RX. This subtracts 1 from RX. So the answer is 1 minus 1 is 0. Well, 0 will set the bit in the flags register. I think it's the ZF flag. And when the JE instruction is ran, it will perform the jump. So this binary right here is 10,000 times it's going to write these 3 bytes. Now, one thing I don't like about what I've done here is that it says 74, which in any other case is a decimal number. Really, I should be doing 0x74. I might have to fix that. But it's basically, it's taking it as a hex number. So hex 74 byte, hex 1, and hex 90. So 74 is the byte code for the jump equal. It's the opcode, I'm sorry. It also needs a secondary byte after it, which is the 01. So these 2 bytes together make up the jump equal instruction. So the 1 is the number of bytes to jump. So it's going to jump 1 byte. And this 90 is the no-op byte, and so it's going to jump the no-op byte. So this is literally 10,000 little jumps. And that's the test. And each one of these tests does a similar thing. Sets the flags register in such a way and issues a different opcode for a different jump. And I don't know, we'll scroll through there if you want to take a look at them. You can stop the video whenever you want. You can see that in order to get the flags register set right, I had to use some different logic here to get it where I needed it to. And I'm not going to go through that. There's my normalized code. Not going to go through that. And my debugger doesn't like my syntax for the binary right. That's why it's kicking that out. And here's the find least function. Take in this array of numbers, go through a loop. Not going to trace that either. Just going to let you see it in case you want to have it. So let's go watch this run a little bit. I want you to see what's in there, how it works in the debugger. Okay, here's the main entry point of the program. We can go ahead and execute a few statements. Pops up the console window. I'm going to drag that off the screen. So here's what the DAD was for. If I right click on here and do search for, oh, it's off the video. Let's try to get that on there. Let's do search for. I don't know if I need to do current region or current module exactly. Might give you the same results, I don't know, but search for a constant in the current module. Not really sure the difference between a region and a module, to tell you the truth. I know this debugger as much as I know it, and I probably know a fraction of what the debugger can do. So I just, kind of get by, I guess. I type in DAD as an expression, and I see all those lines where I'd put, those are all my lines I put. And I can literally, with the F2, turn those into stoppers. Someone will be laughing right now saying there's a much easier way to do it. Well, please put a comment in for me. Alright, so let's run this program. And instantly we hit a stopper. This is our JL, this is our first test. There's our DAD line. What we see here is, if you look down at the flags register when I hit this line, that the ZF flag is 0. Well, it already was 0, but it's still 0. Some of the other bits changed. The JL instruction will use the ZF, and since it's 0, hold on a second here, I might be leading you wrong. Let's go back and look at our screen. I was thinking JE, not JL. So here I was, talking faster than I think. Okay, the JL doesn't compare the sign flag with 1 or 0. It compares it with the overflow flag. Alright, if it's not equal. Let's go back. I actually didn't want to do the JL for the video because I didn't want to get into the mental gymnastics of which bits do you set to perform a jump. All I know is I just like to think simply. Like if your mathematical operation gives an answer that's less than 0, then the jump will happen. So if you got to get into the 2's complement reasoning and the overflow bit to find that answer, and I'm not prepared to do, like I said, not prepared to even make myself think about that. All I know is that the jump is happening, and it jumps 1 byte. It's jumping the no-op. Jump, 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 jump. And it's doing 10,000 jumps. You see these same 3 bytes repeated, 7C0190. So you see the 7C01 is interpreted as the jump less than, and then 90 is the no-op. It counts as, those 3 bytes count as 2 lines of code, 2 lines of assembly. And the debugger interprets it properly, and you see 10,000 jumps. Jump, 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 jump. Okay. Let's run through that, and now we're okay. Now this is going to do this test 1,000 times. It's going to do 10,000 jumps 1,000 times. So I'm going to take the stopper off. I'm going to go full speed, and we stop at the next one, JNE. I'm not even going to go through the bits. I'm not even going to pretend to try to do it. All I care is that I've got it right, and it's doing the jump. Every test is doing the jump. 10,000 jumps, 1,000 times. I guess that's sounds like I want to say million, but I think it's 10 million. Hard to count zeros. It's a lot of jumping. Let's just say, as Trump would say, it's a lot of jumping. Not a good Trump impression. There's the next stopper. I got a whole series of stoppers I'm going to hit here. You can see that the JG is jumping. Another stopper is the JGE jumping. Next stopper, JE jumping. JNE is jumping. JO jumping. And get that off. Not close enough. There we go. That one I had to do some. I had forced me to do some mental gymnastics to try to get the bit set right, JNO, and I got it. It's jumping. JS, jumping. Truthfully, most of these jumps I've never used. I just seem to use the same few jumps over and over again. JNS is jumping. And it looks like the window printed. So, those results are all out of whack because I was stopped while the clock was running. We can run it again. You can see that the size of the executable is 361K, which is quite large, and that's because normally an executable of a test function, a test program is like 5 to 10K. The reason it's so full is because these test functions have like 20,000 lines of code. They're small lines of code, but still counts as 20,000 lines of code. So let's run this full speed, see if we got all our jumps. And go. There's the test. Looks again, JL and JLE seems to be, and JG seem to be just a little slower than the rest. But the others kind of fluctuate. So I guess you could say that maybe they are a little bit slower, like maybe 1 or 2%. But pretty much kind of the same. If you're really splitting hairs, I guess you could say, it does matter just a little bit. There it is. Had an idea. There's the test I made to check it out. It looks like maybe I was a little bit correct, but not very much. So, thanks for watching.